Let's look at a standard parallel plate capacitor. We have two metal plates separated by an air gap, hooked up to a 100-volt battery. Our goal is to figure out exactly how much electrical charge this system can hold. To solve this, we first pull the given variables from our problem. We know the area of each plate, the voltage of the battery, and the standard constant for the permittivity of free space. Then we get our final variable. The distance between the plates is 3 millimeters. This is a dangerous trap. It is given in millimeters, not standard SI units. Before we touch a single formula, we have to convert this distance into meters. Since milli means 10 to the negative third, 3 millimeters becomes 3 times 10 to the negative third meters. If you skip this step and start calculating right away, your final answer will be off by a factor of 1,000. Catching unit mismatches at the data gathering stage ensures your math will actually work. Now we can calculate the capacitance. We'll use the formula capacitance equals epsilon naught times area divided by the distance. Let's plug in those correctly formatted variables. A fraction packed with scientific notation looks intimidating, but we simplify the math by focusing strictly on the base 10 exponents first. We have a 10 to the negative third in both the numerator and the denominator. They cancel each other out perfectly. Next, we look at the standard coefficients. 6 divided by 3 is 2. That massive fraction collapses into a straightforward multiplication problem. Multiply 8.85 by 2, and we get a capacitance of 17.7 times 10 to the negative 12 farads. Writing out 10 to the negative 12 is cumbersome. In standard SI prefixes, 10 to the negative 12 translates to pico, so our final answer for capacitance is 17.7 picofarads. By isolating and canceling your exponents before touching the core numbers, you bypass messy calculator errors and keep complex physical calculations manageable. Now it's your turn. Pause the video and use the formula Q equals CV to find the total charge on each plate. Use the capacitance we just found and our original voltage. Welcome back. To calculate the charge, we revert our capacitance back into base scientific notation. So we multiply 17.7 times 10 to the negative 12 by our 100 volts. Multiplying by 100 gives us a raw charge value of 1770 times 10 to the negative 12 coulombs. Mathematically, this number is accurate. Structurally, it sits in a messy middle state. It violates the rules of standard scientific notation and will lose points on an exam. Proper scientific notation requires exactly one non-zero digit to the left of the decimal point. Right now, we have 4. To fix this, we shift our decimal point 3 spaces to the left. To balance that physical shift, our negative exponent adjusts upwards by 3. That gives us our properly formatted answer, 1.77 times 10 to the negative 9th coulombs. We can clean this up even further. 10 to the negative 9th corresponds to the prefix nano. The total charge stored on each plate is 1.77 nanocoulombs. Here is a unified summary of the formulas and the unit conversions we use today. Take a quick screenshot for your notes. Mastering Class 12 physics requires 2 specific habits: actively managing your units from the first step and applying the strict rules of scientific notation to reach the finish line.